Because I think the numbering system's kind of wonky in these documents. It resets itself.
Yeah, it's easy, moderate, and hard.
Yeah. Okay, which of the following should have the lowest boiling point? Yeah. So this is number one. Lowest boiling point. Let's see, we've got sodium sulfide. The reason I'm going to write these up here is because I'm going to talk about each one. Not just identify the correct answer. And into and H2O. Okay, as far as the lowest boiling point goes, what determines the boiling point of a compound? Based upon what we've studied in the chapter, it's the strength of the intermolecular forces. What's holding those things together in that liquid phase? That's the energy you have to put in, the heat you have to put in to overcome those intermolecular bonds. Then they can leave the liquid into the gas phase, right? So the weakest intermolecular forces, let's put them in order. Strongest, ionic, right? Okay. Then you have dipole-dipole. Or actually you can have dipole ionic. And then you can have dipole-dipole. And then in here, hydrogen bonding is the ultimate dipole-dipole. Right? It's the strongest of the dipoles. And then last but not least, well, yes, last and least, in terms of strength, is the London dispersion. All right, so let's look at our choices here. We got any ionics in there? Yeah, there's an ionic. That's the strongest one, right? That'll have the highest boiling point. Then we've got HF, which is extremely polar. So it's have not just a dipole-dipole, but it's hydrogen bonded. And then ammonia is polar, right? Remember drawing the structure. So it's going to be polar like that. So ammonia is polar. Probably not as strong as this one, right? Because that's hydrogen bonding. This one, nitrogen, dinitrogen, is perfectly symmetrical. It has no polar characteristics whatsoever. So it only has access to dispersion. And remember, everything has London dispersion forces. It's just when these are so strong, they make this one irrelevant. But if that's the only one you have to work with, then that's the very weakest, and this would be the lowest boiling point. In fact, its boiling point is minus 195 degrees Celsius. Anything above that, it's vapor. And then water, of course, is hydrogen bonded. Okay, so we looked at the, let's try this. What if we put them in order of strongest to weakest, right? This would be the strongest, right? This would be the weakest. Let's see, we have 5 of them. That'd be the weakest. And then this would be the next one, right? Then we have the tiebreaker between HF and water. That would be difficult to choose. For one thing, fluorine is more electronegative than oxygen. But water has 2 hydrogens there. So you have 2 possibilities for interaction. So it'd be a flip of a coin for these. I wouldn't venture, well, I could venture a guess. I could put maybe the next strongest would be water, and then you know what? Now I think the next strongest would be the most. This one would be stronger. No, that would be stronger. Is that?
So we're going with water stronger than,
Yeah.
They said
Um,
don't change your original.
Then the,
They said don't change your original answers and you probably right.
if I were taking an exam, yeah, I'd probably miss it. Let's just leave it at that. Okay, any questions? All right. Next, number 3. All right, when a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? If we draw a water molecule, which is bent, and it has 2 lone pairs, remember our Lewis structures. The bond itself between each hydrogen and oxygen is polar that way. Right? So if we just take those 2 bonds, their vector summation is going to be, right, since it's bent, they don't cancel each other out. They actually add together. And you get that way. That gives this hydrogen a slightly positive and this hydrogen a slightly positive, and that oxygen a slightly negative. In addition to these extra negatives up here, that gives your molecule a very polar character. Okay, so how do they interact when they come close to one another? Well, another water molecule comes in like that, perhaps. Right? And since this is negative, we get a bond like that. Okay, so which one of these fits that? Hydrogen from one molecule and an oxygen from the other molecule. Yeah, B is a good answer. That's how they interact. And for any hydrogen bonded substance, this is the trend. The hydrogen is always the positive, and it interacts with whatever the negative side of the molecule is. Now, if this were HF, then that would be fluorine and only one H. But it'd be a similar type of attraction.
you said the hydrogen's always the negative.
No, positive. Now, why is this bond so strong? It's not just the electronegativities, which are significant, but the fact that hydrogen is so small. And remember, the force of attraction is based upon 2 things, right? It's the size of the charge and the distance. So if you can get those charges, those opposite charges closer together, forces are stronger. And since hydrogen is essentially just a proton, right? Most of the time, right? We're not talking about deuterium or tritium here. We're just talking about most of the hydrogens are just protons. They're tiny. So you can get that positive charge very close to the negative neighbor, and that increases the force of attraction. All right. And number 3. And let's scroll to the next one. 4. Okay, 4. Let me shrink this so we can see it all at once. Oops, shrink it again. There we go. So we're going to answer number 4 based upon our Roman numeral 1, 2, or 3. All right, which of the following statements are incorrect concerning drawing number 3? Okay, what do we have in number 3? We've got a chlorine and a hydrogen bound together. All right, we've got hydrogen chloride, right, which should be polar which direction? Yeah, this one. But this is going to be our negative side, this is going to be our positive side. And whenever they come close to each other, got that hydrogen out there, it's going to be attracted to this negative. Okay. So which one of the followings are incorrect? So the first one, electrostatic interactions exist between the molecules. Yeah. Yeah, it's a slight positive and a slight negative. That's true. Molecules, B, the molecules find the best compromise between attraction and repulsion. That's also true. You get this attraction, but if they get too close, then you start, then the nuclei and the electrons start repelling one another. This is a net effect, this slight negative. But you still have the electrons and you still have the protons with their charges. And if they get too close to one another, then they start to repel in excess of the attractive force. Okay, so that's true. B, the molecules find the best compromise between attraction and repulsion. That's always true. These molecules exhibit ionic bonding. Is that true? They're not ions. They're only partially charged. Okay, so C is false. OCS exhibits this type of interaction. Well, let's see. We had O, C, S in here like that. And we drew the Lewis structure. That would be 4. This would be 6, and that'd be 6. So that's 16 electrons. Right? Use up 2 of them. 14. 2, 4, 6, 8, 10, 12. Right? And then 2 more. There. So if we take, we could go either side. Usually, if we're going to put a double bond between them, it goes to the more electronegative one. Right, so oxygen is more electronegative. It's probably on this side. That completes the octet. But when we look at the structure, this is going to be a trigonal planar electronic. Right, with our lone pair up here. Right. That's not right. Right, because we have to have an octet here. We got an octet there. We don't have an octet here. I think I drew that wrong, didn't I? Is that right? 6, 6, 12, 16. Oh, -4. We don't need that. But we do need to move 2 of these over here. There we go. That's better. You see what I did wrong? I was trying to exceed the octet on carbon, not on oxygen. God, you can't do that. Why can't we exceed the octet on oxygen? Because it doesn't have access to d orbitals. It only has p orbitals. So we got 2 for the s orbitals and 6 for the p's. That's the octet. We can't go any further. So everybody in the second period obeys the octet rule. Well, except for boron and beryllium, maybe. They can be less than, but we cannot exceed the octet for the second period. Okay, back to our problem. All right, so we're going to have the bonds are dipole that way, so we're going to have a slight dipole this direction. All right, so this is a polar molecule. It will behave similarly to Roman numeral 3. The same type of interaction. 2 of the above statements are incorrect. No, only one of them. C. All right, before we leave this one, let's look at another one. Number 2 is ammonia. Right, we've pretty much hammered that one to death. How about this one in the top I? Roman numeral 1. Right, we've got a difluorine. A difluorine. It's going to look like this. right? All the halogens. Diatomic, hydrogen's diatomic, 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 diatomic. All those are diatomic. So this is correct. You do have those. But notice that it's labeled as like that and like that. Can that happen? Yeah. It's just that it can't happen for very long, right? Because they're the same molecule. Right? So there's no permanent dipole here. This is a London dispersion interaction, where you temporarily, for a microsecond, have this situation, and it influences the other molecules to become slightly polar at the same time. So if we have another one over here, right, it would influence this one to become negative and this one to become positive, and we get that attraction temporarily, right? So, are any of these below here incorrect concerning one? Electrostatic interactions exist. Oh yeah. London dispersions. Molecules find the best compromise. Yep, they always do that. These molecules exhibit ionic bonding. Nope. Okay. OCX exhibits this type of interaction. Actually, it doesn't. Well, yes, it does. It's just not strong enough, right? London dispersion forces are always there. So I guess technically that's true. Right, so we got the same answer for that one too. All right. Moving on. Let's take a look at number 6. Which best explains the following trends? Okay, looks like we've got all noble gases working down the periodic table. Helium, neon, argon, krypton, xenon. Yep, they're in order. And the boiling points are increasing as we go down. So what explains that trend? Right? They're not polar, right? There's just a single atom, right? So they can't be polar. So what are our options? London dispersion, dipole, hydrogen bond, Le Chatelier's principle. I think I was just searching around for something to throw in that spot. Yeah. Or none of these. London dispersion forces. That's the only explanation. They're a temporary attraction, and London dispersion forces, the magnitude of the London dispersion increases with the size of the molecule, because there's a greater probability for uneven distribution of electron density. You can, on the small atom, the helium, right, there's not a whole lot of space there. So those valence electrons are basically stuck. But as you get bigger, neon, they've got more room. The valence electrons are more spread out. Plus, there's a more probability that they will become unevenly located just for a split second. And the bigger you get, the more likely that happens. You get the same trends for homologous series of hydrocarbons, for example. Right? Right. You know about this because we're talking about it. Right. If you get methane as a single carbon, then you get ethane, say 6, and then you get propane, and keep getting bigger and bigger, and you can go all the way up to say, let's say 25. That's probably asphalt. H 52. The boiling point, melting point, whatever the case may be, increases as you get bigger, because the larger molecules have, one, probability of uneven distribution of electron density around them, and 2, these are all straight chains, so they can lie right next to each other. and you have more interactions per molecule, which increases their boiling point and melting points. So size has a lot to do with how London dispersion forces are expressed. The larger the species, the stronger the interactions. And that's what that increase in boiling point shows us. Got helium, liquid helium, we've never made solid helium, but liquid helium is the coldest substance that we can make and hold in a container. 4K, right? 4 degrees, actually 4 units above absolute zero. All right, 7. Yeah, I didn't have that one marked.
Oh.
I'm just doing the ones I have highlighted, unless you work one that's not highlighted and you have a problem with it, then we'll jump right in. Otherwise, number 7. We're still easy too, I think. Which of the following compounds has the lowest viscosity? All right, we're still talking about interactive forces. Right, CCl, A, B, C, E. And the first one is carbon tetrachloride, which is a liquid. Yep. Nitrogen gas. Water. And then this compound, which is CH3, and then CH2 taken 25 times. 2, 5, and then another CH3. This is a long chain, a long carbon chain, some type of grease. And then hydrogen chloride gas. Okay. A number of ways to approach this. If we're looking at viscosity, what increases the viscosity of any substance? The strength of the intermolecular forces. The stronger the forces, the thicker it is, the higher the viscosity. So if you're in a hurry, excuse me, to get this one solved and move on in the middle of the test. As a general rule, liquids are more viscous than gases. Okay. So we can focus on just the gases, like this gas and that gas. Okay. And believe it or not, you can measure the viscosity of those gases. It takes a special technique, but it can be done. So which one is more viscous? The one that has the strongest forces. So we're looking for the least, right? Mm-hmm. The lowest viscosity. This has technically not hydrogen bonding, but it is polar. And this one's non-polar. So there's your least viscous of all of them. Which would be the most viscous? B. More than likely, yeah. You do have hydrogen bonding here, but this molecule is huge. And even though it doesn't have polar bonds available, it's not polar. It's so monstrous that the London dispersion forces in total along that molecule are sufficient to actually exceed the forces that water experiences because it's so small. All right, so this one would be the most viscous. In fact, I even have my doubts that it's a liquid. It might even be a solid. I don't know why I would put liquid in there. I think the authors of the question put liquid in there. It's very viscous. All right. What about other things? Can you think of other things that would be viscous because of their intermolecular attractions? Anything you might eat? Say on toast or pancakes?
Butter.
Butter, okay, yeah. How about honey? Yeah, or syrup. They have lots of sugar in them. And the sugars have those hydroxyls sticking out all over the place. So you got hydrogen bonds available. All right, number 8. When a nonpolar liquid displays a convex meniscus. 8. A nonpolar liquid displays a convex meniscus. Which of the following explains its behavior? So where are we going to see a meniscus? Inside a tube. So it could be a capillary tube, it could be a larger tube. But the liquid is drawn up into it and somehow, like maybe we've got a suction bulb up there. And if it's a convex meniscus, which means which direction?
In. Or out.
Outer. Convex is like this.
And the other one is called.
Concave.
um,
It's caved in from the top.
Got
If we make it bigger, like this, so that we can say something about. All right, which one of these explains its behavior? It has a low surface tension and therefore clings to the glass. Is that true? We've got a battle of forces going on here. We've got adhesive versus cohesive forces. The cohesive forces are internal among the molecules of the liquid. And the adhesive forces are external. That's why they call glue an adhesive, because it binds unlike materials. So if this is the case, which one's winning? That one. The cohesive forces are winning. They're stronger than the adhesive forces. Okay, so A can't be it. That's just the opposite. How about B? The cohesive forces are stronger than the adhesive. That's it. That's true. And C, the adhesive forces to the glass are stronger than the cohesive. Right, that's the same as A. It's wrong.
Now,
Yeah, go ahead.
would C be true if it was a. When concave?
The other way,
Yes,
like this,
yes.
be just the opposite. The adhesive forces would win then. See, they're stronger. They're pulling the attraction is pulling the liquid up against the walls. And the only thing keeping them from climbing further is mass. Right. So this would be water. Of course, this has to be glass. And this would be, example, would be mercury.
Okay.
All right. 9, 10, 11. Which substance can be described as cations bonded together by mobile electrons? Remember the two theories that we discussed about metals? There's the electron C model, where you've got these positive nuclei of the metal floating around in a sea of electrons. Right? That's the older version. And that's what we're referring to here. Mobile electrons, cations are bonded together by those mobile electrons. Actually, this kind of bridges between that C model, electron C model, and the molecular orbital model. But we're still talking about a metal. So we got a metal in there somewhere. Looks like A, silver. Silver's a metal. That would work. Any metal would answer that question. All right, number 10. Which of the following statements about steel is false? Okay, let's see. A says it contains carbon atoms in the holes of its iron crystals. Is that true? Yeah, it's an alloy. What type of alloy is it? It's an interstitial alloy. So in other words, it has those voids that our Indian lady talked to us about. Those voids are small, but the carbon atom is small enough to fit in those voids. And it forms bonds with the iron molecules and locks the crystal structure in place. So they can't move. That makes it hard. So A is true. The presence of carbon iron bonds in the alloy makes steel harder and stronger than pure iron, which is absolutely true. Pure iron you can scratch with your fingernail. C, pure iron is relatively soft and ductile because it lacks directional bonding. That is also true. It's receiving intermolecular attractive forces among its neighbors, but they're not directional, not like a molecular solid would be. Like all the hydrogens and oxygens in water are directional. They're directed at the oxygen. But in a metal, that's not the case. Very non-directional. D, the amount of carbon directly affects the properties of steel. That's definitely true. You've heard of low carbon steel, high carbon steel. High carbon steel is extremely hard. And it makes a really, really nice sharp edge if you can hone it down. But it's not very tough. In other words, it makes it brittle too. So you can take that blade, if it's high carbon steel sometimes, and you can just whack it on the table and it'll break. So there's a fine line between too much and not enough. Now the Japanese, when they developed their steel technology, exemplified in the katana, they used a combination of steels. Soft steel that they put in the core of the sword and hard steel that they wrapped around it. Now, I don't think when they developed their steel technology that they understood what they were doing on a molecular level, because sword making over the centuries have been developed into an art form. In other words, you had this procedure that you followed, and it was passed down from master to apprentice. And you just did it that way. And if you didn't do it the right way, you come up with a poor product. So they learned to do it a certain way and didn't deviate from that. And they use some, I think they use some spiritual terms for it, like it has this type of character, right? Rather than looking at it from a mechanistic standpoint that we do in the West. Anyway, back to the topic. Yes, the amount of carbon directly affects the properties of steel. All of these are true. Every one of them. Number 11. We can now produce steels with the right combination of iron and additives, not just carbon, but other metals. We can produce a steel that's as sharp as a katana and as tough with a single alloy, rather than having to blend them together like that. Okay, I was on number 11, I think. Which of the following statements is true about P-type silicon? All right, what are we talking about? P-type. P silicon. We're talking about semiconductors. Right?
Using semiconductors.
Semiconductors, yeah. Pure silicon is an insulator, right? Pure silicon is like pure carbon. Pure carbon as not so much graphite, but pure carbon as diamond is a very good insulator. It does not conduct heat or electricity at all. And silicon is similar. If you start off with pure silicon then, and you want to make it only partially conductive so that you can control the movement of charges, then you dope it with a small amount of either elements to the right of it or elements to the left of it. If you dope it with elements to the right, they have extra electrons as compared to silicon. So that's an N type. P type, you dope with stuff to the left, like gallium or aluminum or boron. And that would produce a deficiency. And that would be your P type. So let's see which one of these matches. It is produced by doping silicon with phosphorus or arsenic. Nope, phosphorus and arsenic are to the right of silicon. So they would produce an N type. Protons are the mobile charge carriers. No, I don't think so. Nuclei of atoms tend to stay locked in place. The only thing that can move is electrons. It does not conduct electricity as well as pure silicon. No, actually it conducts better than silicon. So none are true. Right? None of those statements are true. What are the mobile charge carriers, right? We said electrons, right? Electrons for either one. For the N type, we have excess electrons that move. That's easy to understand. But if this is a P type, how do we get electrons to move when we're deficient? Well, actually, electrons from over here move into that hole right there, right? And it leaves behind a positive. So the electrons do move, but in neutralizing that positive, they leave behind a hole. So for convenience, sometimes we say the hole moves. The hole moves from here to here, right? When in actuality, the electron moves from there to there. Whatever works. It's a matter of practicalities. All right, number 14. A solid crystal of sodium chloride is, we look at the answers, right? Soft or hard, low melting point, high melting point, electrical conductivity. Right. So if we have a crystal of sodium chloride, we actually have that, and then one behind and one in front, and then we have sodiums in here. So we have a network of cations and anions. Right. What does that do for hardness? Yeah, it makes it very hard because the forces, in order to make it soft, you'd have to be able to displace those ions, and they do not want to move. They're strongly attracted to one another. So hard. All right, so we can eliminate A, we can eliminate C, we can eliminate E. So it's either B or D. How about melting?
High.
Oh yeah, it's going to be high, right? Those forces are very strong, takes a lot of energy to get them apart. So it's still B or D, high melting. How about good electrical conductor or poor electrical? What do you need to conduct electricity from one electrode to the other? You need mobile charges, electrons, ions, something to move. These guys are locked in place. They are not going to move. So that means they're poor electrical conductors. And that makes D the best answer. Now, how would you get those things? How would you make them move? Bust them up. Okay, you're not far from the truth. You bust them up by melting. Add enough energy to break those bonds. Now the ions are mobile and they will conduct. You can do that either by melting it, like I said before, or you can dissolve it in a solvent of some kind. Separate the ions, the sodium and the chloride ions from each other in a solution, and then they'll move. Water is an insulator also. Until you hit it with enough electricity, enough voltage, that it ionizes. Right? If you can break the hydrogen away from the oxygen, then you get ions, mobile ions, and then it will conduct electricity. So that's why they say, even though water is an electrical insulator, if the voltage is high enough, you can make it a conductor. So in other words, don't take a bubble bath with your and try to curl your hair. Right. If you drop it in the water, you're toast, because there's enough voltage there to ionize the water and it will conduct. Or I'll tell you about my friend in high school. Well, she wasn't a friend, she was in my class. I went to a high school where my father was a teacher, and we didn't have a lot of money. That's why he was a teacher. But most of the kids there, this was a private school in Atlanta. Most of the kids there were rich. They had lots of money. Atlanta, it was the Lovett School. So they had weekend cottages they could go to. And this girl went to her family's cottage up in the woods and was taking a bath and talking to her friends on the phone in a thunderstorm. Lightning strike hit the telephone wire, went down through the wire, through the phone, through her, through the water, into the ground, and she was dead. Yeah. So even though water is an insulator, it can become a conductor. I say, don't stand, if you're playing golf, don't stand in a puddle of water during a thunderstorm. And I used to do that all the time. My brother and I, we were fanatics. We'd play golf in rainstorms. It's like the Caddyshack, right? I don't think the heavy stuff's going to come down for a while yet. But I never sunk hole in one like that. No, my brother was a good golfer. I wasn't. He had a natural swing. I tended to slice into the woods. Which of the following has the highest melting temperature? All right. So we're looking for, if there are any ionic compounds here, that's your candidate. Right. And it looks like magnesium fluoride would have the highest melting temperature. Right, D. How about the lowest melting temperature?
E.
Could be, yeah. Right, that should be P4. You know, it's difficult for me to explain, but actually CO2 would work better. The only reason for that is I know that at room temperature, CO2 is a gas and P4 is a solid. Right. So that would be a really tricky question. If I changed that one to lowest melting point and left it the way it was, you know, then logic would say that P4 would be a nonpolar, would have a lower, would completely nonpolar, would have a lower melting temperature. Well, when in actuality, carbon dioxide does. So, food for thought. If I change that one up, I would change it so that it would be unmistakable. Number 16. Which of these statements is false? A diamond is a covalent crystal. True? Yep. The size of a unit cell of lithium and cesium is the same. Lithium and cesium. Now, since they're both alkali metals, They probably have the same unit cell type. Right? I'm trying to think of what it is. It's I think it's face-centered cubic. Anyway, they're the same. So what would determine the size of the unit cell? Right? We didn't say a whole lot about that in class. Depends on the size of the atom. Right? The bigger atom should produce a larger cell because they're at the corners, and maybe there's one in the middle, or maybe they're on the faces. But in any case, the size of the atom causes the unit cell to be bigger. So this unit cell should be bigger than the lithium unit cell. So B is false. Molecular crystals usually have low melting points. That's true. A molecular crystal would be like what? Ice, right? Made of molecules. It's a crystal, but it's made of molecules. How about metallic crystals are usually good electrical conductors? No, we just talked about that. They're usually poor electrical conductors. Or none of the statements is false. Well, we found a false one. B is false. 17. How would you expect the melting point of carbon tetrachloride to compare to sodium chloride? Carbon tetrachloride and sodium chloride. Melting point. Which one would have the lowest one? Right, that's ionic. This is molecular. And it's nonpolar. Right. So which one matches that? It should be lower because sodium chloride forms an extended ionic crystal lattice, whereas carbon tetrachloride is covalently bonded small molecule. That's a good excuse as any. They're not both ionic solids like B says. And it shouldn't be higher. And it shouldn't be higher, C and D. How about E? It is not possible to say anything about their melting points without more information. All right. It's tempting to do that, but we know, based upon what we studied about intermolecular forces, that this one's going to have a lower melting point than that one. Right, let's see, 19 and 20. At normal atmospheric pressure and a temperature of 0 degrees C, which phase of water can exist? Right. We've got a pressure of 1 atmosphere and a temperature of 0 degrees. Temperature 0. Oops, backwards. 0 degrees C. Okay. What phases of water can exist?
Is this what you talk about when you say you take distilled water and distilled ice and then get an equilibrium at 0 degrees?
Yep. Yeah, at 0 degrees, you're going to have a solid ice, liquid water. Yep. And we could look at our phase diagram and draw the same conclusion, right? Temperature here, pressure there. Let's see. The triple point here, and we're going down here, we're going up like that, then we're going like this. So this is solid, liquid, gas, and it's 1 atmosphere pressure. So this is 1. That's that shouldn't be there actually. This would be 0 degrees C. You're on the phase line when you do that. So at a higher pressure, the temperature would be lower to have solid and liquid together. Or if you have liquid and gas at 1 atmosphere, you'd be out here maybe at 100 degrees. That would be liquid gas at 1 atmosphere. But if you increase the pressure, then the temperature on that phase line would be higher because it's a positive slope. All right. Actually, remember I drew you a hexagonal structure for ice? That's why the density decreases for ice. Actually, the density of water, let's see, density of water versus temperature. Density of water versus temperature. So if this is liquid, as it gets colder, the density increases. Let's see, temperature this way. So as it gets colder, the density increases to about 4 degrees C. And then from 4 degrees C, you start to get that hexagonal organization kicking in. Now the density decreases to 0 degrees. So the maximum density of liquid water occurs at 4 degrees C. You don't have to know that from the test. Throw that one in for free. 20. Which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? All right. Remember when I drew a gas, let's see, liquid over here, let's put liquid over here, solid over there. And if you go from liquid to gas, that's evaporation. And if you go from gas to liquid, that's condensation. If you go from liquid to solid, that's freezing. Sometimes it's called fusion. And if you go from solid to liquid, it's called melting. And if you go from solid to gas, that's sublimation. You go from gas to solid directly, that's deposition. Those are the different phase change processes that can occur. So which process must exist in equilibrium with evaporation when a measurement of vapor pressure is measured? If you're measuring vapor pressure, you got a liquid down here and the vapor phase above it, and they're in equilibrium now. So if this is liquid and this is gas, liquid gas, evaporation has to exist in equilibrium with condensation. Okay. So that would be vapor pressure is what we would be measuring there. All right. Okay, 21. I've already used up an hour and we're still in the easy ones. 21. You're given the following boiling point data. Which one of the liquids would you expect to have the highest vapor pressure at room temperature? Okay, vapor pressure is that property that is inversely proportional to the strength of intermolecular forces. So the weaker the forces, the higher the vapor pressure. And you can tell from the boiling point the relative position of intermolecular forces, right? The lowest boiling point will give you the highest vapor pressure. So which one would that be? Diethyl ether? Yeah, diethyl ether would give you the highest vapor pressure. At room temperature, what would give you the lowest vapor pressure? Ethylene glycol. That's the stuff you put in your radiator. Keep it from freezing in the winter or boiling over in the summer. That's a different property. That's colligative property. Okay. So the principle there is vapor pressure increases with decreasing intermolecular forces. Have we got to one that you had trouble with yet? Okay. Which of the following decreases as the strength of, well, that's kind of a repetitive, right? The vapor pressure of a liquid decreases as the strength of attraction increases, right? 23. In which of the following processes will energy be evolved as heat? I should have left that diagram up there. So when you evolve energy as heat, that's exothermic. And what you're doing is you're going from a higher kinetic energy to a lower kinetic energy. And that could be from a gas to a liquid, or a gas to a solid, right? Or a liquid to a solid. All of those would be exothermic. They would give up energy. This side has more energy than that side. Right, so when it goes from here to here, it has to give up energy. So which one of these matches? Let's see. Sublimation is endothermic, goes the other direction. Crystallization gives up energy. Crystallization. Let's see. That's not one of those phase changes, is it? Crystallization we normally think of as a bunch of ions in solution getting together and forming a precipitate. But that is also exothermic crystallization. Oh, we found our answer. Vaporization, you got to put energy in. Melting, you put energy in. Rather than draw that one on the board, let's see if we can talk about it there on the picture. Oops. There it is. There was a bit of a delay with the Zoom server, I imagine. Choose the correct statement about the diagram below. Okay, so we've got a phase diagram, pressure on the y-axis, temperature on the x-axis, and we have a phase line between solid liquid, liquid gas, and solid gas. We see the triple point where all of those three lines meet, and then we have a 1 atmosphere line. Okay, now let's see what the questions are. Correct statement. The diagram is qualitatively correct for water. True, false? No. The solid liquid phase line is a negative slope for water. For most materials, the line is positive slope. Right? But for water, it's a negative slope. So that one's not correct. B, the diagram shows that the melting point of the solid increases with increasing pressure. So which line are we looking at for the melting point? The one we were just talking about, right? The solid liquid line. So as the pressure increases, the temperature of melting also increases. That line has a positive slope. So B is correct. C is false because the triple point is below 1 atmosphere, not above. D, the diagram could represent the phase diagram of CO2. I don't think so. It's not cold enough. All right, so we found our answer. How about 26? Get another look. A different look at a phase diagram. Apparently. Okay, below is a phase diagram for compound Q. You wish to purify a sample of Q that was collected at 1 atmosphere pressure and 100 degrees K. Maybe I better draw this one. Got pressure here, temperature there, and this temperature is in K. And this pressure is in atmospheres. Okay. Then we have a straight line that goes up to about right here. Then we have it, it takes off like that, goes up like that. And then we have one that takes off like this. Yeah. Okay. So this one is going to be about 1.5 atmospheres. 1 atmosphere is going to be about right in here. And zeros, half is about right here. And this is 0. Okay, temperature. This is about 200 right here. So this would be 100. And this would be 300. Okay. All right. So our Q was collected at 1 atmosphere and 100 K. 1 atmosphere and 100 K. So we collected Q right there at that point. And what does that mean? That means in this part of the graph, it's a solid. It's not a liquid. It's not a gas at that point. We have Q is a solid. Right. So if we want to purify Q by subliming it, in other words, we want to purify it by going from solid to gas. How would we do that? Well, you have one possibility is you could just decrease the pressure at that same temperature. Sublime it. But that would be a little difficult to manage. Right? It was probably a colossal effort to get that temperature down to 100 K to begin with. So now that we have Q, it might be easier to get down here to where you can cross this line with temperature rather than pressure. So if we decrease the pressure to something like here and then go that direction, then we could sublime it. Okay. So do we have one that looks like that? Increase the pressure. No, increasing the pressure is the wrong direction. Increase the temperature to 300. If we went to 300 from here, we'd make a liquid, right? That won't do it. That's not subliming. Lower the pressure to 0.5 and increase the temperature to 200. So that's what I did here. But that works. Increase the temperature to 300 and then lower pressure to 0.5. No, that doesn't sublime it. Okay. Abandon your attempt. Just throw up your hands and walk away. No, we're not going to do that. So the best answer was C for that one. That's essentially what we do when we freeze dry things. The fancy word for that is lyophilize. I used to maintain, 1, 2, 3, 4 lyophilizers in my past life. We would take plant material usually and freeze it in liquid nitrogen and then stick it in the freeze dryer, and you draw a vacuum, very, very low pressure, and then add just a little bit of heat from below. And in 24, 48 hours, depending on how much stuff you put in there, you'd end up with freeze-dried leaves, plant material. The nice thing about that is you've removed all the water, which essentially preserves it, and makes it easier to grind. And you haven't damaged any of the metabolites that are stored in the cells. So, and that's what we were getting at. We wanted to know what's in the cells. Okay, so let's move on. We got other phase diagrams in there. Okay, how about this one, 29? That one has a familiar look to it. Right, the solid liquid line is negative slope, so it's probably water. So which one of these is false? The solid has a higher density than the liquid. Right, if this is water, then that's definitely false. The solid has a lower density. The rest of them must be true. When heated at 1 atmosphere, this substance will first melt, then boil. That's true. And that's what water does too. All right. Moving on. Okay. Now we're in moderates. Moderate. Number 1. Yep. Which of the following is the correct order of boiling points for CHEM102? It might be easier to read it this way. Methanol, right? Wood alcohol, that's the one you don't want to drink. C2H6, ethane, and neon. Okay. So, correct order of boiling points. And it looks like we're going from low to high based upon the answers, right? The carrots go to the left. So the lowest boiling point should be first. That's got to be neon. Highest boiling point, your ionic compound. Right. So then, let's see, we need to decide, how about these two? The higher boiling point is going to be the one with the polar character. In this case, hydrogen bonding. So this one is going to be here. That one, ethane, should be here. Okay. That would be D. Let's see. Number 4. Does this have calculations? Looks like it. Did this one give you trouble? No? Okay. Assume that 12,500 joules of energy is added to 2 moles of water. Right. So the amount of energy, the heat that we're going to use is 12,500 joules. The mass of the water is 2 grams, which is the number of moles, then would be about 36 moles. Okay. Let's see.
It says 2 moles and 36 grams in parentheses. So you got me.
Oh, that's what this means.
Okay.
Right. If you took 2 grams of water and you want to convert it to moles, right, you need the molar mass of water. Actually, it's 18.02. 36 is close enough for our work.
Okay.
The reason it gives you both of them is because the heat of fusion is given in kilojoules per mole. So we'd use this value, and the specific heat is given in terms of grams. So you need both of those to do the calculations. Let's see, the molar heat of fusion for water is 6.02. So the molar heat of fusion is 6.02 kilojoules per mole. Yep. And the specific heat of water is 4.18. 4.18 joules per gram degree C. Okay. After all that heat is expended, and we're starting with ice at 0 degrees. Okay. And there's no liquid water with it. We're starting with the solid at 0 degrees. So I like to draw a picture. It helps. So let's see. Temperature over here. Degrees C. And this is added heat. So as we increase the amount of heat, we go from 0, we go from here below somewhere down here, go up to there. Right? When we get to 0 degrees, it starts to melt. Right? And we don't get any change in temperature here. This is all solid. This is solid and liquid. Then once we get to all liquid, we can heat the liquid again. And that goes up to, it's about right here, to 100 degrees. And then we flatten out again. So this is all liquid. This is liquid and gas. And then once we use up all the liquid, we can heat up the gas. We can get superheated steam, in other words. Okay, so if we're starting right here, right, with 2 grams, then how do we determine how much heat is being used? We need the heat of fusion, this one right here. So the amount of heat used for 2 grams, 36 moles. 36 moles times 6.02 kilojoules per mole equals, whatever that is. 36 times 6.02 is, do that again. I don't like that number. Is 216.72 kilojoules, right? Moles cancel. Okay, but this is in joules, right? So let's convert this to kilojoules, to joules. Well, that can't be right. We don't have enough heat. Let me see if I did that right. Kilojoules. 36 moles. Oh, I got it backwards. Sorry about that. It's 2 moles. No wonder that didn't work out. So that's 12.04 millijoules. All right, now we're back on track. Okay, everybody see where I flowed? Okay. All right, convert that to joule because this is in joules. 3 places to the right, correct? Right, as the unit gets smaller, the number gets bigger. So it's got to be 12.040 joules. Okay, so if we started off with 12,500 joules, what do we got left? Minus 12,040 equals 460 joules. Okay. Now, that's all the heat we got left. So what formula are we going to use now? Well, we're heating a liquid, right? So we've got our Q equals S times mass times delta T. Remember that one from calorimetry? There's our specific heat. 4.18. I'm going to leave the units out because I'm running out of room. And we got a mass here of 36 grams. Right? And then delta T. Well, actually, delta T can be broken down into initial, final minus initial. So what's the final temperature? Well, we don't know that. But the initial temperature is 0 degrees, right? Once all the ice is gone, we're still at 0 degrees, and we start heating it. -0. So this value here is 460 joules. Right, so we can solve for temperature. What's our final temperature? So let's see, 460, or it's already in here. I'm gonna divide by 4.18, right? Bring it over here. And then divide by 36. And the temperature now, after we've used up all the heat, since that's 0, then the answer is temperature is 3.1 degrees C. So what do we have there? Only water. Right. We're still right down here. No solid, just water.
So did you like round up, because I'm getting 3.05.
Yeah, I just rounded it up.
Okay.
Let's see. Yeah, 2 significant figures here, so I kept 2 there. Now, what if we wanted to know how much energy is required to get us to boiling? We used up enough energy to get us to liquid. Now, how much energy do we go from here to boiling? Well, in that case, the difference in temperature now would be 100 minus 0. And then we would solve for the cube, correct? So let's see, 4.18 times 36 times 100 is 15,048 joules. It would take that much energy to go from here to there and start boiling. Right? So we've already used up 12,040. Right? Add those together. Let's see, 8, 8, 0, 7, 27. So if we had exactly 27,088 joules, we get to the boiling point. Right? So anything greater than that would take us through here and maybe into there. We'd have to figure out how much. What we'd need then is the heat of vaporization, which wasn't given. All right. Moving on. See here, what do we got coming up? Ooh, difficult. All right. A crystal was analyzed with X-rays having 2.33 angstrom wavelength. The angle of the first order diffraction, n equals 1, was 19.2 degrees. What would be the angle for the second order diffraction? All right, so the wavelength is fixed. We're only using 2.33 angstroms. Let's see, this is number 1. The wavelength is 2.33 angstroms. What's an angstrom? Did we go over that? An angstrom, 1 angstrom is equal 10 to the minus 10 meters. A nanometer is 10 to the minus 9. So an angstrom is 1/10 the size of a nanometer. It used to be a commonly used value. I guess some people still use it. Let's see, the angle of the first order. So the angle of the first order is equal to 19.2 degrees. 19.2 degrees. That means n equals 1. We want the angle of the second order. That means n equals 2. Okay, that's how I keep things straight. Pull it out of the problem, put it on the board where you can make sense of it. Okay, we're gonna need the Bragg equation. And so if you look in the back, useful information. Where is the Bragg equation? Looks like it's in the middle of the third column. In lambda to be sine. In lambda to be sine theta. So the distance here is the distance between the layers in the crystal. This one is here, there. This one changes. This one stays the same. The distance in the crystal doesn't change. It's fixed. The angle changes. So the thing that varies is this one and that one. Now you have two options. What you can do is solve this equation for that one right there, using the first order information. That's probably the easiest way to do it, unless you really just love algebra. Then you could set up two equations and solve them for the this in the second order, right? Do it all at once. But I detect from the grimaces on faces that it's better to do it in two steps. Okay. So in this case, we're going to take n equals 1. Lambda equals 2.33 angstroms. Then you got the 2, this is constant. Then you got the distance here, right? That's our unknown. And then the sine of angle, 19.2 degrees. Okay. So if we solve for our unknown, right, then we've got 2.33 angstroms. And we're going to divide by 2 on this side, 2 over here. And then we bring the sine of 19.2. Did I do that right? D. So bring the 2 over here. Yep. Bring the sine over here. Yep. Okay. So you have to just find out where the sine function is on your calculator. And I'm going to take 2.33 and divide by 2, and then divide by the sine of 19.2. So got to find my sine function. Here it is. And then divide that in. So let me write the sign down here just in case. 3, 2, 8, 8, 7. Right. So the distance is 3.542 angstroms between the layers. Okay. Now we set up a second equation. This was the first order. So the second equation would have n equals 2 now, times the same wavelength, angstroms, equals 2 times this value, which now we know 3.54 angstroms is D, and then sine theta for the second order. Now our unknown is theta, the angle. All right, so let's put these over here. Let's just keep where they are. Be less confusing. Bring the 2 over here, and 3.54 over here, and that's sine theta for the second order. Okay, so angstroms are going to cancel, and that's 1. So we actually only need to divide 2.33 by 3.54. And I get 0.6577 equals the sine of theta. Okay, how do we find theta? It's not technically the inverse of sine, but in order to find the sine of theta equals this value. So if you have that value in your calculator, you want the, and on your calculator is probably arc sine or a sine. which would be raise the function above sign. So if you look on your calculator, but one button says sign and right above it in different colored letters is a sign, arc sign. So if I press that one, then now theta, oops, not Q, theta of the second order is 41.1 degrees.
What's the arc sign look like?
Mine just is ASIN. Uh-huh. Yours might be sine to the -1.
Yes.
There you go.
How do you do it? You don't press the second?
Yeah, you have to, right, you have to promote it to the function.
You said sign -1 arc sign, those what it's gonna look like?
Yes.
So you put the number in first?
Yeah, put the number in first. I assume, you got algebraic calculators, I'm not sure. You may have to say arc sign and then parentheses and put in the number.
Yeah.
In trouble with that one.
41.1. Right, is it in scientific notation?
It is.
Okay. Yeah. That gets me sometimes. I forget that decimal point. Okay. Oh. And let's see, we're down to number 2. Chromium metal crystallizes as a body-centered cubic lattice. Chromium is going to look like we have chromium here, here, here. 1, 2, 3, 4, 5, 6. And then there's going to be a chromium in the middle. Okay. If the atomic radius of chromium is 1.25 angstroms. So if R equals 1.25 angstroms. What's the density of chromium in grams per cubic centimeter? So we're looking for density in grams per centimeter. All right. So looking for density, density equals mass per unit volume. Mass is going to be in grams, volume is going to be in cubic centimeters. So let's tackle the volume first. What's the volume of that unit cell? Useful information. Body-centered cubic. BCC. That's just above the Bragg equation. A equals 4R divided by square root of 3. 4R divided by square root of 3. And this is what they call A. That's the length of the side of this cube, A. So if we find out that value from this radius of the atom, then we just cube it, and that gives us the volume. Okay? Did I lose you? Well, we're good, okay. So it's 4 times 1.25 angstroms divided by the square root of 3. So let's see, 4 enter 1.25 times, and then 3 take square root of 5. Okay, I get 2.8868 angstroms is the sign on that cube. Now, we're going to have our volume in centimeters, right? So before we start cubing and squaring and messing with our values, Let's change this to centimeters. So then when we cube it, we get cubic centimeters. It'd be easier to do it that way first. So how would we do that? 8, 8, 6, 8. And notice I'm keeping a lot of decimal points here to avoid rounding error. So if it's that many errors on that many angstroms, then we want to convert it to centimeters. We want to cancel the angstroms, but I don't know the relationship to angstroms and centimeters. So I'm going to go to meters first. Right. So 1 meter is 10, excuse me. 10 to the minus 10 meters is 1 angstrom. Right? Okay. But now I want to convert meters to centimeters. Right, and I have 10 squared or 100 centimeters per meter. So all right. Now if these are canceled, I've got centimeters. Now I can just say, all right, 10 to the minus 10th and 10 squared gives you what? 10 to the minus 8, correct? Add them together, minus 10 and 2. 10 to the minus 8. 2.8868 centimeters. Now we can get the volume. That's the side of the cube. Volume equals cubed. All right. So let's see. There, I've got it in there. 10 to the minus 8 centimeters. I want to cube it. So my calculator, I need to do this and this. So the volume is 2.406 times 10 to the minus 23rd cubic centimeters. So that would go in here. Mass divided by 2.406 times 10 to the minus 23 cubic centimeters. Now, what does that represent? That volume. That volume represents a certain number of atoms, correct? So how many atoms are in that unit cell for a body-centered cube? Remember? You got 1 in here that belongs to that cell, nobody else. Right? How about these guys? Each one of these chromiums at the corner belongs to 8 other cells. 1, 2, 3, 4, 5, 6. Excuse me, 1, 2. Oops. 1, 2, 3. Well, there's some out. 1, 2, 3, 4, 5, 6, 7, 8. So you got 8 of them, but only an eighth of each one belongs to the cube. So that means only 1, right? An eighth times 8 is 1. So that's 2 atoms of chromium for that cell. Okay, what's the mass of 2 atoms? We've done that before. We did that in the first semester. Right? Atoms. How many atoms in a mole? 6.022 times 10 to the 23rd atoms per mole. Right? Now we've got atoms out of the way, we've got moles. Now we can convert moles to grams. What we need is the molar mass of chromium. Let's see. 52.00 rounded off. There we go. So that should give us the mass of the chromium in that unit cell. .022 exponent third divide and 52 times. So I get 1.727 times 10 to the minus 22 grams. That's the mass of chromium in that unit cell. And this is the volume in that unit cell. 1.727 times 10 to the minus 22 grams. So if I divide that by this, I get rounded off to what? Three significant figures. 7.18 grams per cubic centimeter. That would be B. Okay. So this whole process hinged on this relationship. Mass of chromium in the unit cell, volume of the unit cell. We had to solve both of those problems first before we could solve this one. Have to be very methodical about it. I was going to use another word, but it wouldn't be polite. Okay. Let's see who's next. All right, we finally got to chapter 11. Let's see, how much time do I have left though? 11:15. I got a half hour. Let's see, this is going to be 11 and that's going to be easy. Lemon. Okay. Number one. A 0.1 molar solution. 0.1 molar solution of, oops. Sodium chloride. I assume that's aqueous. Which one of the following would be closest to 0.1? Now, we could go through the trouble of taking 0.1 and converting it into mole fraction, mass percent, and molality. But to save time, this is moles per liter of solution. Molality is moles per kilogram of solvent. All right. Remember, water is a density of 1 gram per milliliter, which means a liter of water is a kilogram of water. So these are roughly equal as long as the solution is very dilute, which it is. So these two would be very close to one another. This might change a little bit. Kilogram of solvent would be less than liter of solution in terms of absolutes. So the actual molality would probably be a little bit less than molarity. No, greater, excuse me, greater, because this is going to be small. Smaller makes this great. So it might be 0.1000001. The rest of them we could calculate, and actually I do in the worked problems. But in the interest of time, that gives you the justification for saying these are roughly the same. All right, number 2. This is the definition. Which of the following concentration measures will change in the value as the temperature of the solution changes? All right. The only one that's going to change is the value that incorporates volume. Temperature affects volume. It doesn't affect number of moles. It doesn't affect mass. So mass percent won't change. Mole fraction won't change. Molality won't change. Molarity will change with temperature because it has incorporated volume in its calculation. And 3. Which of the following chemical or physical changes is an endothermic process? And so, well, you got to put heat in to get the change to occur. Evaporation. Yeah. Right, you put heat in and you break those bonds. That's an endothermic process. Combustion of gasoline obviously is exothermic. Right? Just put your hand on a hot engine and find out. The mixing of sulfuric acid and water, that's definitely exothermic. Right? If you mix concentrated sulfuric acid and water, it's going to get hot. I mean, really hot, depending on how much water you've got. That's why the rule is do as you ought to, add acid to water. In other words, add your concentrated acid to a lot of water, and that will make the temperature change, the absolute temperature change, small. Same thing works for bases. If you try to dissolve sodium hydroxide pellets in water, it will get hot. All right, so that's exothermic. Freezing of water. As water freezes, it has to lose energy to do that. Go from a liquid to a solid. So that's an exothermic process also. The only endothermic process in there is evaporation. Four. Which statement about hydrogen bonding is true? Well, let's see. What are our choices? Hydrogen bonding A is the intermolecular attraction forces between two hydrogen atoms. I don't think so. How'd this one get in here? I thought we already covered hydrogen bonding.
We didn't.
Yeah. So we'll just go straight to the answer. Hydrogen bonding arises from the dipole moment created by the unequal sharing of electrons within certain covalent bonds within a molecule. That's true. How about those others? Hydrogen bonding interaction between molecules are stronger than the covalent bonds within the molecule. No, that can't be. Intermolecular forces cannot be stronger than intramolecular. Otherwise, you tear the molecule apart. And we skipped over C. Hydrogen bonding of a solvent molecule with a solute will not affect the solubility. I beg to differ. It has an enormous impact on the solubility. Like dissolves like. Hydrogen bonding capabilities of water molecules cause, see, that's butane, to be more soluble in water than, no, methanol is more soluble because it has the ability to hydrogen bond, like butane doesn't. All right, so easy answer. Five. Which of the following favors the solubility of an ionic solid in a liquid solvent? Well, like dissolves like. So, okay, the answers tell us that we're looking at lattice energy, solvation, large polarity. Okay, we're gonna have to look at these individually. C and then D and E are all or none. D is all, E is none. So we have to look at A, B, and C separately. A large magnitude of solvation energy of the ions favors the solubility. What's the solvation energy? It's the energy that's given up when the solvent molecule and the solute molecule interact. It's that stage 3. Remember stage 1, 2, and 3? Right. This one is endothermic. This one's endothermic. This is where, this is the solute bond breaking. This is the solvent bond breaking. Or make a hole. And then when you put them together, this is exothermic, where you form the bonds between the solvent and the solute. That's the solvation energy. If that solvation energy is large, that means there's a strong attraction between these two, and that favors the formation of a solution, right? So A is true. A small magnitude of the lattice energy of the solute. it takes just a little bit of energy to get these things apart, that would favor the formation of a solution. How about C? A large polarity of the solid. Yeah, if it's an ionic solid, a large polarity would tend to actually be the same thing as A. Large polarity would give you a large solvation energy, right? So all of them are true. So there you go. Here. And how about this one? 6. I don't know why 6 ended up in easy. 6 is not easy. 6 is difficult. Solid potassium fluoride has a lattice energy of minus 804 kilojoules per mole and a heat of solution of minus 15. Rubidium fluoride has a lattice energy of minus 768 and a heat of solution in water of minus 24. Which salt forms stronger attractions with water? All right, if we've got KF and RBF, those are the two. KF here, yeah, RB, yeah, here. And we want to make a solution out of each one of them. So the 3 steps that they have to go through, we have to, let's put these in terms that are given in the problem. Lattice energy. Lattice energy is the energy that it takes to break these bonds. Okay, so the delta H lattice is required, right? And then the let's see, heat of solution. The heat of solution is actually a combination. The heat of solution is a combination of the let's see, delta H of the solvent. In other words, make whole. And then this one is the delta H of solvation. In other words, attraction of these individual ions to the water molecules. So this delta H that's given to us is heat of solution. This delta H of solution is a combination of these two. All right, so when the question is, which salt forms a stronger attraction with water, this is the one we're focused on right here. If we want to answer the question, I mean, we do need a quantitative approach, but this value is the same for both of them, right? So if we can calculate this one, then it will account for the differences here between the two, okay? All right, so let's see. Lattice energy is minus 804 for the KF. Lattice energy. Okay. Lattice energy equals minus 804 kilojoules per mole. And lattice energy over here is minus 768. Minus 768. Okay. And then we're given heat of solution minus 15 for this one. So this delta H of solution equals minus 15, did I say? Yeah, minus 15. And the other one's minus 24. is minus 24. A mole. All right. I don't want to waste you guys' time, so I'm gonna have to look at how I solve the problem. Hmm. Okay, I messed up here. This whole expression is the heat of solution. Those two together, this is the delta H for a better expression is expansion. In other words, make a hole. And then the heat of solvation is when they come back together. So this is our second approach. This is our first. This is our third. And this value goes in here for each one of those. And let's see. All right. So I need to focus on the signs here for a minute. This value says that overall, that expression gives us an exothermic process. It gives up more heat. This one gives up more heat than that one does. But the lattice energies are different. So are the lattice energies positive or negative? Well, if the lattice energy is negative, the lattice energy is negative because it expresses, let's use this example. That ion gas and this ion gas comes together to form this solid. Okay. That's why it's negative. It's exothermic to go from here to here, but we're not going that way. We're going from here to here. We're going backwards, right? So in this expression, that needs to be a positive value. So minus 15, and these are all in kilojoules. Yeah, minus 15 equals 804 positive plus a delta H, which is the combination of these two. Okay, so this delta H is equal to, let's see, I should be able to do that in my head. Let's see, comes on this side as negative, should be 819 kilojoules, minus 819 kilojoules. And on this side, it's minus 24 equals plus 768 plus delta H. So delta H is equal to minus. It would be 792 kilojoules. Negative. Okay, so which one gives up more energy from this position right here? That one does. KF gives up more energy in this process. And since that's the same for both of them, it's due to the solvation or the attraction of water molecules to the individual ions. So to answer your question, KF has the stronger attraction with water since it has more negative heat of hydration. This is the heat of hydration. Okay. All right. That looks like an extra credit to me. If I were to use something like this. And that's a difficult problem.
Can I like say like, it might be stupid and this might be completely wrong, but if you just add 804 and 15, that equals the same as if you were to work out that entire problem.
Uh-huh.
So can I just do that? Or if I do it on a different problem, it's gonna be completely wrong.
If it's built the same way as this one, with the values represent the same variables, then yeah, you could just add the numbers together.
Okay.
The reason I went to all that trouble was because of what each one of those numbers means. In reference to our 1, 2, 3 steps.
Yeah.
And the 2 and 3 steps are combined together to give us our answer. Right, because the heat of expansion is the same for both of them. Right, they're both going into water, so it's the same amount of energy that expands the water to make room. Okay, number 7. Yeah, you can need a new one. Oops. Okay, dip into my bag here. Okay, use the following drawing of a gaseous solid in equilibrium with a solution. Which of the following statements are true when the piston is pushed down? So if we've got a cylinder here, and we've got a liquid there, and let's see, the gaseous solute up here is not the same as this material. We're not talking about evaporation. We're talking about dissolving that gas in that liquid. Okay. So if we put pressure on it, what's going to happen? Right, Le Chatelier's principle. We haven't talked about that yet, have we? Okay, forget that. What's going to happen? Well, if we decrease the volume, that means, according to the kinetic molecular theory, that means there are more frequent impacts of that gas molecule against the liquid, even if the temperature stays the same. More frequent impacts means more of that gas is going into solution. So, C, this will cause the pressure of the gas to increase and the concentration of the dissolved gas to go up. Yes. And vice versa, if we went the other direction, if we expanded it, more of that gas solute would come out of solution, because now we would be decreasing the number of impacts, and the equilibrium will shift toward moving those gas molecules out of solution until we get a balance again. It's all equilibrium, rates of the process. Coming out of solution, going into solution. They will eventually balance. All right, number 8. Which of the following correctly states this relationship between temperature and the solubility of a substance in water? All right, solubility of substance in water with temperature. If you're putting a solid in solution, then usually solubility increases as temperature increases. Usually, not always. There are some cases where it goes in reverse. How about with a gas? When we put a gas in solution, the solubility decreases as temperature increases. Always. No exceptions. Okay, so how about our statements here? Solubility of a substance in water with temperature cannot be accurately predicted, especially for ionic solids. Well, that's true. That was C. A, the solubility of a substance in water increases as the temperature rises, especially for gases. No, it's the other way around. So A is false. Solubility of a substance in water decreases as the temperature rises, especially for ionic solids. We can't say that either because it's variable. And D, solubility of a substance in water decreases as the temperature lowers, especially for gases. Well, it works for gases. No, the solubility as you decrease the temperature increases for gases. Right, so D is false also. The only true one in there is C. Yeah, C is the only right answer in that whole bunch. All right, number 10. A solution contains 1 mole of liquid A and 3 moles of liquid B. This solution has a vapor pressure of 314 torr. Liquid A has a vapor pressure of 265 and liquid B has a vapor pressure of 355. Okay, so that was my first thought. When I looked at this, I said, okay, so you got A and B together, right? If one of them is volatile and the other one's not, then it doesn't matter. But they're both volatile. So now we have to use the modified equation. My mind's going blank. Reynolds law. Modified Reynolds law. Which says that the total vapor pressure is equal to the mole fraction of A times its pure vapor pressure plus the mole fraction of B times its pure. Okay, that's if you have two components. If you have more than two, then you just string it out, keep going. I'm sorry?
Add or something, is that a, okay, add.
Yeah, add them together. The mole fraction of A times its pure pressure and the mole fraction of B times its pure pressure, then you can add them together and get that. Okay. So if this solution is ideal, in other words, the attraction between A and B in solution is about the same as A with A and B with B, that's an ideal solution. And the vapor pressure diagram right? So if A increases this direction and B increases this direction, then as the concentration of A increases, then the pressure is going to go up. And as the concentration of B increases, its vapor pressure is going to go up. And the combination of the two is the connection between these two lines right here. Now, if A and B repel one another when they get in solution, then you're going to get a positive deviation. Okay. If they attract one another, you're going to get a negative deviation as the total pressure, total vapor pressure. Okay, so let's take the numbers and do a little calculation here. So the mole, you have 1 mole of A and 3 moles of B. So we have moles of A equals 1, moles of B equals 3, correct? Okay, so the mole fraction of A equals what? 1/4, right? 1 divided by 4. Because the total is 4. mole fraction of B is 0.75. That makes sense because you add up the mole fractions, they have to be 1. If you've accounted for everybody. Okay. So now we're also given the pure vapor pressures of A is 265. Pure is 265 torr. And B is 355. 355. Torr. Okay. All right. And the vapor pressure of the mixture is 314. So we're given 314 here. What we want to do is calculate what this would be if it were ideal. Okay. What would it be if it were ideal? Well, we substitute 0.25 here and 0.75 here. And see what that is. Okay. Let's see, 265 times 0.25 and then 355 times 0.75. And add them together. And I get rounded off 333. That would be the ideal vapor pressure compared to the actual. So the actual is less than. So this is a negative deviation. Right? The actual vapor pressure measured is 314, and the ideal would be 333. Correct? Okay. So that's a negative deviation. Let's see what our questions, our answers are. This solution exhibits positive deviation. Nope. Negative deviation of Raoult's law. It's not ideal. All right, so B is the answer, the negative deviation. Somewhere in here, let's see, A would be 0.25. It'll be here, about right there. This would be 0.25 and this would be 0.75 mole fraction. So right in here somewhere. If we add these two together, we should get that place right there. But we're actually getting this one right here. That means it's a negative deviation. The actual is less than the theoretical. Okay. I'm looking to clear up the frowns.
So because
Yep.
the 333 is higher than 314, it's lower. Because the 314 is less than the 333.
Right.
correct?
This is ideal. This is actual.
Okay, so but if it was lower than 314, then it would be
The other way.
the other way. Okay,
Mhm.
okay, I think I understand now.
Yep.
And it gets the negative because it attracts, is that what you said earlier?
Yes. Uh-huh.
Okay,
Yeah, A and B must attract one another. Because if they're more attracted in solution than they are separate from one another, then they tend to suppress the evaporation of each of their components.
I'm picking up what you're putting down there.
Okay, everybody, can I erase it? Okay. Oh, I'm over time. Let's see how many more we got to go. 12, 13. Easier to look at this one. Okay. 1, 2, 3, 6. I got 8 more to go. It may not take a whole lot of time, as long as we don't have to do any calculations. Number 12, a cucumber is placed in a concentrated salt solution. What will most likely happen?
The moisture will come out of the cucumber.
Right, we got a cucumber here. So I'm drawing a few seeds. Okay. And this is concentrated salt. We'll just make it sodium chloride. Right. So this is a hypertonic solution, which means it's higher in solute concentration than in the cucumber. Conversely, it's lower in water concentration. So if there's more water in the cucumber, it's going to come out. Yep. And that would be water will flow from the cucumber to the solution. Yep. It will shrivel up. It will become nice and flaccid. Right. It won't make a crisp pickle.
Butternut and bacon.
All right. 13. Osmotic pressure depends on all but which of the following? All right. Osmotic pressure, which is the symbol pi. Right? And it's related to what? Molarity, gas constant, and temperature. Yeah, temperature. Now, the one factor I didn't put in here was the Van Hoff correction. Okay, based upon this, that's pressure depends on all but which. Does it depend on atmospheric pressure? No. It depends on the molarity of the solution, the temperature of the solution, the ratio of moles of solute to solution volume, which is another way of saying molarity. So atmospheric pressure is independent of atmospheric pressure. All right. 14. Shaving cream is an example of which of the following colloids? That's probably the easiest one. It's a foam, right? Foam. What would be an example of an aerosol? Hairspray, right? Liquid suspended in a gas. You can have a solid aerosol too, smog. That might be better classified as a sol, rather than an aerosol. Emulsion. What's an example of an emulsion? A liquid in a liquid, right? Milk. Yeah. No, milk is a good one. Yeah. What happens? Well, a coagulate is not a colloid. That's what happens to a colloid when you disturb it. If you heat it, many cases, or if you add an electrolyte, like salt, or if you add an acid, which is probably technically an electrolyte. I got a lesson, a practical lesson in coagulating a colloid the other day. My wife has a Keurig that she uses to make coffee, and she also just heats water up to make tea. So she hadn't used it in a while, and it looked pretty nasty. So I said, I better clean this thing out. So I took the reservoir and filled it with vinegar and ran vinegar through it several times. And then I put water in it and cleaned it out. Well, apparently I didn't clean it out well enough, because I heated up the water to make her tea, and I dropped a tea bag in it, 3 minutes. And then she likes milk in her tea. So I put sugar in, and then I added a little milk, and the milk curdled because I still had vinegar in there. So I cleaned out the bowl and ran 3 or 4 more cycles through and made some more tea. It was obvious. I mean, it happened like that. I mean, that colloid was gone. Okay, moderate. What number? 3. Okay. A 0.2 molar solution of solute X in benzene. So the molarity is 0.2 molar in benzene. All right. Displays an osmotic pressure given by the formula 0.1 RT. Which of the following is most likely the case? All right. What does that value represent? It represents I times molarity, doesn't it? Van Hoff correction factor times the actual molarity of the particles as they exist in the solution. So if this is equal to 0.2, right? Excuse me. No, that's equal to 0.1, sorry. Yeah, this is equal to that value right there. And we know this one is 0.2. Then what's I equal to? I has to be 1/2, right? 1/2 of 0.2 is 0.1. So what does 1/2 mean? I mean, we know what happens when you put a, say a salt in solution and it breaks up into its ions, like sodium chloride breaks up into 2. So I would be 2. But what happens when it's 1/2? It's the other way around, right? When our solute goes into solution, it actually forms pairs. Okay, so to answer that question, X exists in benzene as X2. It forms pairs to do that. Now, of course, that's a difficult question. But if the value here is, say, 0.4, right, then we know I is 2, for example. That's a tricky question. All right, number 4. Which of the solutions, 0.1 molar sodium chloride, 0.15 molar glucose, and 0.1 molar calcium chloride would have the highest vapor pressure, boiling point? Okay, so we got these 3 solutions. 0.1 molar calcium chloride. Oh, sodium chloride first, excuse me. Sodium chloride first. Let's keep them in order. And then 0.15 glucose, 0.15. That's molal. Sucrose. And now 0.1 molal calcium chloride. There we go. Okay, vapor pressure. How do they compare? We're looking for highest vapor pressure. Well, the vapor pressure, remember, decreases as the concentration increases. Right, so the higher concentration will give the lowest vapor pressure. And the lowest concentration will give the highest vapor pressure. So the lowest concentration here, this is equivalent to 0.2 molal ions. This one doesn't ionize, so it's still 1.5 molal. And this one is the same as 0.3 molal ions. Okay, so the vapor pressure is highest for the lowest, sucrose. Right? So sucrose gives us that one. What's the other one? Boiling point. We want the lowest boiling point. The lowest boiling point is going to be the largest concentration. So that would be this one. So it'd be 0.15 molal sucrose and 0.1 molar calcium chloride, which would be, oh, wait a minute. I get it backwards. Highest vapor pressure. Okay, that's right. D. Lowest boiling point. Oh, yeah. The boiling point, excuse me. The boiling point is closer to pure when the concentration of the solute is low. This is the lowest concentration of solute. Yeah, so D is the correct answer. Lowest boiling point is correct. Both of them. Highest vapor pressure, lowest boiling point. If we increase the concentration, we increase the boiling point. Oh, we got the same 3 or 5. So. What's the question? Lowest vapor pressure. Lowest vapor pressure would be this one, correct? Be the highest concentration. And the lowest boiling point would be this one again. All right, so this one would be calcium chloride and sucrose. Or glucose, excuse me. Why did I write sucrose? Yeah, that's right, C. It's probably as I'm getting in a hurry. All right. And this is difficult. One, two. A solution is prepared from 53.8 grams of non-volatile, non-dissociating solute, 85 grams of water. The vapor pressure of the solution at 60 degrees is 132 torr. The vapor pressure of water at 60 degrees is 150 torr. What's the molar mass of the solute? All right. So what do we got going on here? 53.8 grams. We're looking for the molar mass of the solute. And we're given the mass of the solute, 53.8 grams. Okay. So if we're going to do the molar mass, we have to know how many moles that is. Right. This is non-dissociating solute. Right, so we don't have to worry about the Van Hoff correction. And going into 85 grams of water. So this is the mass of the solute. This is the mass of water. 85 grams of water. The vapor pressure of the solution at 60 degrees is 132 torr. The vapor pressure of water at 60 degrees is 150 torr. So we're decreasing the vapor pressure. All right. Since this is non-volatile, then we have a total pressure equal to the mole fraction of water times the pure pressure of water. Okay, Raoult's law. Okay, what's the total pressure of the solution? Is 132 torr. We don't know the mole fraction, but we do know the pure water vapor pressure is 150 torr. Right? So the mole fraction of water equals 132 over 150. Correct? So if I did that right, 0.88. What's the mole fraction of the solute? The mole fraction of the solute equals 1 minus 0.8. So that's equal to 0.12, right? That's the mole fraction of the solid. All right. So how many moles of water do we have?
You gotta do the 18.
You gotta convert it, don't we? Grams, moles, 18.02. Right, because we can't work from grams. I mean, this is all in moles. 85 and 18.2. I get 4.1, 4.717 moles of water. Okay. You know, we didn't have to do this right here. This mole fraction is equal to mole fraction of water is 4.717 moles of water divided by the total number of moles, 4.717 plus the moles of the solute, correct? That's the total moles. So far? Okay, so now we can solve for the actual moles of the solute. I didn't need this right here. I mean, we could use that, but this works just as well. All right, so let's see. 4.717 equals 0.88 times that, which is 4.151. 151 plus, what's that? Plus 0.88 times the moles of the solute. Okay. Now 0.88 N equals that one minus this one.
Where did you get the 4.151?
Oh, this one times that. Right, because I got to take this whole thing, come over here and multiply it times 0.88.
Oh.
Right.
So that gives you.
And that gives me this term here. This one times that one is this value. This one times that one is this value. Okay, now I'm going to solve for the unknown. So I think this one is positive, over here is a negative. I subtract that from 4.717, which is 0.566. 0.566. And then I divide both sides by 0.88. Which is 0.643 moles of N. Okay, so the molar mass is this mass of our solute, 53.8 grams per how many moles? 0.643 moles. $83.6 grams per mole. Is that one of our choices?
Yes.
Okay. That's good news. Now, is this one where you couldn't figure out where to put what?
Yeah, but
Okay.
you didn't help me any.
Okay. This type of problem, it helps to go to the end.
Yeah.
What's the question? What's the molar mass? We're looking for values to go in here for mass and moles for the solute. We got the mass already. That's given to us. Now we have to find out the moles of solute. And based upon the vapor pressures that we're given, right, we'll use Rayleigh law to find out what's the mole fraction of water. The mole fraction of water then is this value, which comes out of that.
Mhm.
But then this is also the moles of water divided by the total moles. That's the mole fraction. So that's where we got the total moles, right? Moles of water divided by moles of water plus the moles of solute. Now we have an equation in that unknown. And that will give us this value right here.
Okay, and you divide. Or you times,
Yeah, I took this whole expression.
Yeah.
Right. But technically, we multiply both sides by that expression.
okay,
So it canceled this side and gave it this side on that. So 0.88 times that plus 0.88 times that. That's where I got this. Right there.
okay.
And that's equal to 4.717, which was left on this side.
Mhm.
Now I just solve the unknown.
Okay, I got you.
Let's see. Okay, that's the last one. Ooh. This one's gonna take some doing.
Is there any way I can go ahead and get my test and you started out
Sure.
outside the door?
Yeah, no problem there.
I'm gonna leave this stuff right here. Just grab it and hand it to me when you're done. It's my next.
Okay.
Crosswords.
Yep. Let's see, so I don't forget my place. There we go. Let's see, here we go. All right. So we've got a 10.4 gram mixture of table sugar and salt. We don't know how much of each one. We just know the total mass.
Which is 10.4, right?
We don't disturb. I'm sorry?
Which is the 10.4.
Yes, that's the total mass. Mass of the mixture equals 10.4 grams. 40 grams. Okay. When the mixture is dissolved in 100 grams of water, the freezing point is found to be minus 2.24. So the mass of water or the mass of the solvent is equal to 150 grams. And the freezing point depression equals minus 2.24. How do I know that? Because pure water freezes at 0 degrees. So the change in temperature is minus 2.24. Okay. Calculate the percent by mass of sugar. All right, we have to use a little algebra here. We got to say X, let X equal. Remember that. Okay. So let X equal mass of sucrose. Why did I say that? Because calculate the percent by mass of sugar. Okay, so I'm going to let X equal that. Once we find X, then we can calculate the percent based upon that mass and this mass total. That means 10.40 minus X equals mass of sodium chloride. Okay. Now, next we want to use this relationship to find out what the molality of the solution is. Right. So if we have the change in temperature, and this is going to be absolute, is equal to the let's see, I forget my symbols. We'll use the correct symbols. There it is. Here it is. K sub F times molality times I. K sub F times molality times I, Van Hoff correction. Now we know that we're going to need a Van Hoff correction because that right there will split into two. The KF is not given, so you have to look in here. KF for water is 1.86 degrees C per kilogram mole. So KF for water is 1.86 degrees C per molal, which is the same thing as 1.86 degrees C kilogram. Molals in the denominator, so moles per kilogram, they would be flipped. That's why kilogram ends up on top and moles at the bottom. Okay, here's the tricky part. We have to split this equation into two parts. In other words, we have to include the effect of the molality of sucrose times I, plus the effect of sodium chloride times I. And there are two different I's there. That's the real trick for the problem. Knowing that you can do that this value is additive for these two expressions. If you don't know that, then just hand in your paper. Okay, so this delta T, which is 2.24 degrees, 2.24 degrees C, is equal to that case of F, 1.86, and I'm going to leave out the units. And the molality of sucrose is our unknown. And I is equal to 1 because sucrose does not dissociate. Then we get 1.86 here times the molality of sodium chloride times 2 because it does dissociate. All right. I think I'm on the right track. Okay.
So that is negative 2.24.
No,
No.
it's absolute.
Okay.
Right, okay. In order to determine molality, we're going to need molar mass for sucrose and for sodium chloride. Sucrose is C6H12O6, and sodium chloride is whatever. So let's calculate the molar mass for each one. Let's see.
You
Car-
have
yeah.
you have C12H22.
Oh, sucrose. I'm sorry, that's glucose. Thank you.
You're welcome.
12, 22, well, correct.
11.
11. Trouble today. Okay. So now we can calculate the molar mass. 12 times 12.01, right? 12.01 times 12 is the carbon contribution. Then 22 times 1.01, and add that together. And then 11 times 16. Add that together. 342.34. 342.34 grams per mole. And sodium chloride is 23, yes. 23 for sodium and 35.45 for chlorine. It's 58.5 grams per mole. Okay. What we want to end up with is mass of the sucrose. So if molality is equal to, now this is, I better do this. So you can get the M's confused. Molality is moles of solute per kilogram of salt. So this is 150 grams, which is how many kilograms? 1, 5, 0 kilograms. 1, 2, 3. All right. So the molality of sucrose is going to be the moles of sucrose. If the mass of sucrose is X, then the molality of sucrose is equal to convert this into moles. So if we convert moles here, X grams times grams per mole, 342.34, like that. So this is equal to X divided by 342.34. That's the mass of X. Actually, that's the moles of X. Because we cancel grams. That's the moles of X. So the molality is the moles of sucrose divided by the kilograms of solid. So this is X divided by 342.34. And then divided by 0.150 kilograms. That. The same thing for sodium chloride then would be 10.4 minus X divided by 58.5. And that's also divided by 0.15. Okay, so there's the molality. Now, if we substitute this value in here, this value in there, you'll get a big equation. And I'm running out of room. So let's see if I can squeeze it in here. 2.24 equals 1.86 times this value, which would be, let's reduce this to something manageable. If this is in the denominator of the numerator, it's also in this denominator. So 342 times 0.34, right? This is the denominator, that's the denominator. So we can multiply those two together, can't we? Okay, I got one nod. No? Yeah. Let's see, 342.34 times 0.15 is 51.351. So this is X over 51.351. X divided by 51.351. And then I is 1. Plus, now we have 1.86 times this one. And this is 58.45 times 0.15. This is 8.768. 8.68 in the denominator and 10.40 minus X in the numerator. This is 10.40 minus X over 8.768. This is times 2. Okay. Okay, let's see if we can reduce these any further. Divide this one into 1.86. One, 2, 4 equals, and this becomes 0.0362 X. Okay. And then this one becomes, let's see, 1.86 times 10.4. times 2 is 38.69. That's this term, that term, and that term. Now, this term also has to be multiplied by that one and that one. So that's a minus 2 times 1.86 is 3.72. X. 2 times this one times that. And then this one is still in the denominator. 8.768. Okay. Now this one can be reduced further also. That divided into this and that divided into that. So this is equal to 4.412 here minus 0.424x. And this is 0.0362x. Okay, so we can combine these two. Let's see. Go. And 0.0362. So this is equals 4.412 minus 0.388x is equal to 2.24. So if I take this one and put it on this side, it becomes negative. And 2.24. So this becomes over here. This becomes negative 2.172 equals negative 0.388x. All right, so now all I have to do is divide this one into that one, and that's equal to x. That gives me a positive value, thank goodness. .59 grams. So if I did that right, that's the mass of sucrose and the percent sucrose, unless I made a calculation error somewhere, 5.59 divided by 10.4 times 100 should be the percent. %53.8. Yeah. Close. Rounding error. I know, that's a lot of work.
Is that gonna be a bonus?
It would have to be.
Okay.
Yeah,
That's,
I would
you
require
kind of
something like
lost
that.
me a little bit here and there.
I figure if I was going to lose you anywhere after we came to this conclusion right here, that's the crux of the problem. Then from then on, there is potential for calculation errors because we have to fill in these values.
I got lost at the fraction down here.
That's where I got lost.
Over here.
Yeah,
Yeah,
that's where you lost.
Okay, this is based upon this calculation up here.
Yeah.
This is the number of moles of sucrose,
Mhm.
right? Mass divided by molar mass, grams per mole. Grams cancel, give you moles.
yeah,
Okay, so the molality though is moles per kilogram. So I take that expression here as moles divided by the kilograms of solvent, which is 0.15. And that's what this gives me. Now, in order to get this one, that's in the denominator. This is in the denominator, so I multiply that one times that one and gives me this value.
Okay.
Okay, and I did the same thing for sodium chloride, only it was a little more complicated.
Yeah, that's the one that I got lost on that one, because you have the 10.4 minus the 5, and that's a denominator.
This is, yeah, 10.4 minus X. And this one times that one, just like we did up here. And that puts 10.4 minus X over the product of those two.
Okay,
Then I take those and stick them in the equation. This equation right here.
Yeah.
And from then on, it's be very careful not to make math errors.
So how did you get the 3, 4, 2, 3, 4? Like, I understand it's part of the,
Oh, molar mass,
yeah.
12 times 12.01
Okay.
for carbon. And then 22 times 1.01 for hydrogen.
Oh, okay.
And 11 times 16, add them all together.
you can get them all off of.
Okay, I get what you're talking about now. Okay.
Yeah.
I understand now. And you add them all together and that. Okay.
Yep.
I was just confused because you're talking about, like, I saw the 12, you're like 12 times whatever, and I was like, what's he talking about?
You get those off of the period.
I was kind of skipping a step, I guess.
Okay, yeah, I get it.
I didn't walk over here and point. Okay, so let's see, what do we got coming up?